Já, pode começar.
Okay, so good morning, everyone. So today we are going to talk about the Hodge conjecture and the classical context. So last lecture, Hossein presented to us a version of the Hodge conjecture, which was a more algebraic version. And today we are going to talk about it on the context of differential forms and the Rham cohomology and well, it's the more usual way I would say to present the Hodge conjecture, but it's important to have both both versions of the conjecture in mind. So, well, where are you seeing everything?
Yeah.
Okay. So I think maybe this is better. So, well, in this lecture, we are going to present the Hodge conjecture stated, but we won't prove much of the results we are going to use, but the idea here is to give the main ideas of how we can state the conjecture and what are the concepts involved and everything like this, and the main theorems. So first, I'm going to give some background, some ideas of what we are going to do. So first, we are going to define what is a differential form. So a K differential form is a smooth section of the exterior power of the cotangent bundle. So it's a K, it's an antisymmetric form with K entries, so K linear antisymmetric form. So of course, which varies smoothly with every point. So in local coordinates, we can write it as this, so functions times dxi, where I is a set of indexes with size k, and this means we are just considering the wedge product. That means of each dxi1, dxi2, dxik. Those are simply the dual bases of the cotangent bundle, and the wedge product is the usual wedge product in the exterior power, right? So, and then we can denote the space of all k differential forms as omega k of x. And we have two natural operations: the wedge product, which is just the usual wedge product in the exterior power. So, if we consider the skew-symmetric algebra of forms on each point. And also we can define the exterior derivative, which in coordinates can be defined like this. So if we have a function which is a zero form, right? We are considering this I equals 0, so we will have just a function. So in a zero form, this df can be defined as simply the derivative of f. So this is exactly the element in the tangent bundle corresponding to the derivative of f, right? And then for a general form, we can just take each function fi we have here and compute the derivative of this function and make the wedge product. So this will get us a k plus 1 form, right? So this is the definition of the operator d, which is called exterior derivative. Okay. Then we can define the de Rham cohomology, which is, well, it's just consider the complex of differential forms with operator D. Of course, it's important to say that D squared is 0. So here, for 0 forms, it's simple. It's easy to see that D squared is 0 because we have that the second derivative, like d del squared f del xj del xi, is equal to del squared f del xi del xj if we change the order. But if we change the order here, we will change the order of the differentials here, and changing the order in the wedge product is the same as changing the sign. So everything will cancel and we have d squared equals 0. And then if we consider forms like this, it's even more simple because here the functions multiplying everything are 1, and d of 1 is 0 because of this formula, right? So d squared is 0, and then this defines a complex. And of course, we can compute the cohomology by the natural formula that defines all cohomology. It's important to say that this kernel here, that means the forms that goes to 0 by d, those forms are called closed forms. And this image, the forms that are d of someone, are called exact forms, right? So we are going to use this terminology, closed forms and exact forms. This is important. Okay, so everything we did until here was on the real context. So we were just considering normal smooth manifolds and real coefficients. So everything was real, and now we are going to go to the complex context. And the complex of differential forms, a complex differential form is a section of the stereo power of complexified cotangent bundle. So instead of consider just the cotangent bundle, we consider the cotangent bundle, the complexified cotangent bundle. That means we are taking the tensor over with C. But this means, if we are going to simplify, that we are just taking our coefficients over C. So these functions are still smooth functions. So we are not considering anything holomorphic. We are just considering smooth functions. But instead of smooth functions to R, we are taking smooth functions to C. And of course, if we have a complex manifold, we can define, we have coordinates dz and dz bar, and we can write our form in coordinates like this. So a function fjl and dzj, dzl, dz bar l, where j plus l is k. I wrote this twice, sorry, but of course, we can always write our forms like this. And the important thing is that the number of zj's and z bars, the number of z's and z bars will give rise to a terminology. So we call omega pq form if j has size p and l has size q in this formula. So we are just saying how many coordinates have z and how many have zl bar, right? And so those are the PQ formulas. And of course, we can always consider the de Rham cohomology the same way. We are going to omit the C here because always as all of our manifolds will be complex, every de Rham cohomology will be over C. So you're just going to omit this C from now on. Okay. And so, of course, these, as dZj and dZ bar are linearly independent because, well, the way they are defined using x, dx, and dy. So they are linearly independent, and that means we can define a decomposition of this space omega k. So we can consider omega k as the sum of omega pq for every k, which is sum of p plus q. And also this decomposition will induce a decomposition of the map D as D prime and D double prime, where D prime takes a PQ form to a P plus 1 Q form, and D2 primes PQ form to a PQ plus 1 form. So, I mean, this is just considering this decomposition here. And also, if X is projective, we can consider this theorem, which is a very famous theorem and not easy to prove. So, if you have a smooth projective variety, we can define this HPQ, which would be closed PQ forms divided by exact PQ forms. And then the theorem says that we could just decompose the cohomology in these sets, right? So in a certain way, this is the same as, I mean, this is a very important theorem, and we are going to present two versions of the Hodge conjecture. One of them will use this decomposition, right? So this is important.
Felipe,
sorry.
I'm not sure about this HPQ that you defined, but it is better to define it as elements of the de Rham cohomology which are represented at least by one PQ form. So
right, okay.
They might be exact, but not. There must be mixed PQ in the exactness. I mean, D of some of some PQ. Anyway, I think it is safer to say that HPQ is the subspace of the Rham cohomology, whose elements has a representative, has a PQ differential form representative, something like that.
Okay. Yeah. Okay. Right. It's okay. But yeah, so now we are going to start the important part. I mean, we'll start stating the conjecture. So first we have to define what is an algebraic cycle. So we can consider a closed subvariety with complex dimension m over 2 for some integer m, right? And then, of course, if Z is smooth, we could consider its orientation class, and then it would induce a class in the singular homology just by inclusion, because Z is inside X. But if Z is singular, we can't do this way, so we have to consider a resolution. And now Z tilde, which is singular, which is smooth, sorry. And then, of course, this has an orientation class, and we can include the orientation class by projecting with this map and then including on X, right? So, anyway, in both cases we can define a class here, and we can call this class like Z, this bracket Z, and we start, and now we can make this definition. So an algebraic cycle is a cycle which can be written as this combination of these classes Zi for some subvarieties of X, right? And these cycles are the examples of Hodge cycles, which are going to define, or the main examples of Hodge cycles, which are going to define in the next 2 slides. And the important thing about these cycles, one of them, is that they satisfy this proposition. So if we have an algebraic cycle and a PQ form, which with P plus Q is equals M, okay, of course, because we want to make this integral. But with P different from M over 2, that means P and Q are different. We have that this integral is 0. So why is this? The proof is really simple. It's because if as Zi has dimension M,
omega must be closed. Then you have.
Yeah. Sorry. Yeah. Because sorry. As Zi have dimension M, the only M forms over Z are M over 2 forms. I mean real dimension M. So we would have that all the Zij's and the Z bars. We have to have all the Zij's and all the Z bars in this formula for as Zi has dimension M. And then as we are going to compute this integral by the pullback of the inclusion, and this preserves the decomposition, we conclude that these forms have would be 0 because they wouldn't be M over 2 because we have this hypothesis. So everything is going to be 0. So that means that this proposition is just the fact that we don't have forms with indices higher than the dimension. It's really simple, and it's similar to what Hussein did in the algebraic context. So now we can define Hodge cycles, which are just the cycles that satisfy the proposition. So for every omega PQ form, we have the integral being 0. So those are Hodge cycles. And I mean, of course, they have to be closed. These omegas. So all torsion elements are of course Hodge cycles because by linearity they are going to be 0. That the integral is going to be 0. And the question of the Hodge conjecture, which we arrived at here, is that okay? So is every Hodge cycle? Is every Hodge cycle an algebraic cycle? So I mean, of course, we have the torsion, so we have to consider for any Hodge cycle, is there an integer a such that a delta is an algebraic cycle? That's the question. And I mean, we could just consider everything over Q, and then this A would be just the denominator of the Q linear combination. And also this conjecture, as everyone knows, is one of the millennium problems of the Clay Institute, and it's worth $1 million. So now I'm just in this last 2 slides, just consider the Hodge conjecture in the cohomological language, which is the way it's stated in the official problem statement from the Clay Institute. So, and I mean, it's interesting to see another version of the conjecture. It is actually the same version, but I mean, it's interesting to see the relationships and everything. So if we consider a complex manifold of codimension P, a complex subvariety of codimension P, we can define a cycle H2n minus H2P as we did before. So if this is singular, we can consider the resolution. If it's smooth, we can just include the orientation class. And then we can define this is a cycle in this homology. And by Poincare duality, we can define a class in H2P. So this is just Poincare duality. And of course, this we can include this cohomology in the de Rham cohomology. So this is an element in the de Rham cohomology. And using the definition of the duality map of the Poincaré duality, we have that the integral of a form on Z is the same as the integral of this form wedge this class on X. So this is the definition of Poincaré the duality map. And of course, by the proposition we did here, we have that this integral is 0 if omega is not n minus p n minus p. And so this implies that this class has to be PP because if it's not PP, we would have that we would have some DZJs here and dizzy. I mean, we would have a form which is not n minus p, which would complete this one, and then we would get a non-zero integral here, and this would contradict with the proposition. And also conversely, we have that if this is PP, we would have that this omega is n minus p, n minus p. And by analogy, we can call these elements here algebraic classes if they are a combination of these classes of these forms CL of Z, and Hodge classes all the elements which are PP, because of course in this case the proposition would be satisfied. So I mean this is the same. This makes sense with Hodge cycles, right, and algebraic cycles. So Hodge classes are just these elements here. And algebraic classes are the classes which are combinations of CL of Z, rational combinations. And now we can state the Hodge conjecture. It says if X is a projection on singular variety over C, then Hodge class is a rational linear combination of classes CL of Zi for some algebraic cycles, Zi. And this is the version of the conjecture stated there. So I mean, it's the same version. We are just applying Poincaré duality. But I mean, I think this version here is a bit more geometric because we actually are looking at the cycles and the integral over them. And here we are just looking at the classes in the cohomology, which is maybe more easy to compute and everything. But it's you lost a bit of the intuition, I think. I mean, both versions are useful. And of course, we have many other versions of this conjecture. For example, the one Hussein presented. And well, that's it. So those are my references. So this is the official problem statement on the Clays Institute that Pierre Deline wrote. And the version of the integral, the first version is the one Hussein presents in his first book on Hodge theory. And well, that's it. Thank you.